In this section, we're going to look at the natural exponential function. The natural piece of this just means that we are dealing with a special base. You remember that we could have an exponential function that was 2 to the power of x or 3 to the power of x. Well, the natural exponential function has a very special base. We call that base e, and e is approximately equal to 2.7182821828459. This number down here, just approximately equal to that. Now, E is actually, you'll find it on your TI-84. There is a button, in fact several buttons that have E on them. There are 2 or 3 different ways of arriving at this special number E. One way, which is useful when it comes to calculus, is to look at the graph of y equals 2 to the power of x, the graph of y equals 3 to the power of x, and to look at the slopes at any sort of point. If you look at the slope right here of y equals 2 to the power of x, it's just 0.69. But if you look at it of the slope at y equals 3 to the power of x, it's 1.10. It so happens that the slope, if you have y equals e to the power of x, at this point at 0, 1 is exactly 1. In fact, not just that, but the slope at any point along y equals e to the power of x is the same as the y value itself. So if the y value here is approximately 8, the slope of a straight line at that tangent at that point is going to be 8. If the y coordinate here is 10, the slope at that point is going to be 10. So the slope is e to the power of x as well as the y coordinate. And it's a very special function to allow that, and it's very useful if you do calculus sometime in the future. Now, that's not the only place that e comes up. E also occurs, in fact it first occurs when we're considering continuous compound interest. Compound interest happens a little bit like the compound interest we had before, except it's not just compounded every year, not just every month, not just every quarter, not just every day. Imagine compounded every hour. Well, more often than that. Imagine adding the interest every minute, or every second, or every millisecond. If you imagine you're adding interest after shorter and shorter periods of time, after a thousandth of a second, after a millionth of a second, then, well, that's getting close to what continuous compound interest would be. And if we studied that in a little bit more detail, you'd be able to find that an alternative definition of E is whatever this thing here is, right, 1 plus 1 over a all to the power of a, whatever happens to that as a gets really, really large. And you can see this table here. If you plug a equals 10 into this thing, we get 1 plus 1 over 10 to the power of 10. It gives us this value. But then if you try a equals 100 in here and here, you get 2.7. If you try a equal to 1,000,000 in there, you get a value that's very, very close to the value that we find from the calculator, this value here. So the bigger the value of a, the closer we get to this special value. It converges on this special value e. And a way of writing that is this down here. We can define that number, special number e, to be the limit as x goes towards infinity of 1 plus 1 over x all to the power of x. Now, in order to apply what we know about e, we really need our calculators, and you need to find the button that says e to the power of x on it. It will be this. You have to press the second function and then press the button that has ln on it. So e to the power of 2x, e to the power of 2.5 If you do that on your calculator, it should be 12.18 approximately. So check that you can do that. You might want to then round that a little bit to 4 decimal places, for example, 12.1825. The same thing, when you do e to the power of negative 2, just put a negative 2. Remember to use the negative button way at the bottom of your calculator and not the minus button, which is above the plus. So use the negative button way down at the bottom next to 0, and you'll get this value here rounded to 0.135 to 3 significant figures. So your calculator helps you with e to the power of. It can also graph e to the power of, it can graph exponential functions when you're graphing this type of thing here, y equals e to the power of x, or y equals e to the power of minus 2x. You just go to the y equals button and do y1 equals whatever function it is you need. You should end up with these kinds of functions. Again, the asymptotes for each of these is the x-axis. They almost get to the x-axis, but not quite. Now here's a kind of practical question, quite a difficult question involving the natural exponential function or exponential functions in general. Here we've got the population of the city of Geneva being just this number in 2010, growing to this number in 2012. Now, if we assume that the population is growing exponentially, we can then estimate when the population is going to be bigger than 250,000, bigger than 250,000. So, an equation that would model the population of Geneva would be the general exponential function here, a times b to the power of t. Now, to figure out what a is straightforward. We just have to plug in t equals to 0. So we imagine that the year 2010 represents t equals 0. So in 2010, t equals 0. So p of 0, right, the population after 0 years, in other words, in 2010, is equal to 187,500, and that's equal to a times b to the 0. b to the power of 0 is 1, so we know that a is equal to this value here. Now, to figure out what b is equal to, we use the second population, 192,385. So we have this population after 2 years is equal to a, which we found out already, 187,500, times b to the power of 2. We're just putting what we know back into this equation. We've got a, we found it in over here. We don't know what b is, but we know that t is equal to 2. So we've got an equation here. We can solve that then for b. If we do that, we should get b squared equals this. Simplifying that a little bit, should give you 1.01294. That's our b. So our equation in the end is going to be this thing here. We found our a, then we found our b. So this is our equation. Now we're not quite finished yet, because we've got to find out when, right, in what year we'd expect the population to be 250,000. So we need to solve this equation here. We need to solve the population equal to 250,000. Not particularly easy to do at this stage, because we haven't done what we call logarithms yet. But we can simplify that equation a little bit, so it becomes like this. What you can do to solve an equation that looks like this is put y1 equal to this thing here. So just do y1 equal to 1.01294 to the power of x. go to your y equals button and enter that. And then go to the top right of your calculator, there's a button that says table. If you scroll far enough down the table, you'll see x equals 22 gives you y1 equal to 1.32, x equals 23 gives you y1 equal to 1.34. So somewhere between 22 and 23 gives you that 1.33. So it's going to be 23 years after 2010. In other words, in 2033, the population should exceed 250,000.